Thank you, everyone. And now we're going to start the first keynote session of SBMF 2022. And it's a real pleasure to introduce Valdivino. So Valdivino received his PhD in applied computing from the National Institute of Space Research, INPE, in Brazil. He has a master degree and bachelor degrees in electrical engineering from Federal University of Ceará. He was visiting scholar developing postdoc research at a computational optimization and learning lab, School of Computer Science at the University of Nottingham in England. And he also develops research in formal verification of probabilistic systems at the Concordia University in Montreal, Canada in 2015. So Valdivino has over 25 years of professional experience in working in research and development of aerospace software and systems. He has been receiving several awards at international and national conferences in the fields of computer science and engineering. His main research interests include artificial intelligence, deep learning, machine learning, optimization via hyperheuristics and meta-heuristics, and software testing. He is the coordinator of the project Classificação de Imagens via Redes Neurais Profundas e Grandes Bases de Dados para Aplicações Aeroespaciais, which translates to image classification via deep neural networks and large database for aerospace applications, IDeepS. Okay, so the IDeepS project is supported by the National Scientific Computing Laboratory via resources of the S. Dumont supercomputer. So without further ado, please, Valdivino, the floor is yours.
Let's share my screen. Can you see my presentation?
Yes, we can.
Are you listening okay?
Yeah, we can hear you well.
Okay. So first of all, I would like to thank you very much for the opportunity to talk in this Right Reputation conference, the SBMF. You know that this is a national but with international reputation conference. It's a great honor for me. And I work at the National Institute for Space Research in Brazil. Just to be clear that if it's someone overseas, very fast about our institute, National Institute for Space Research in Brazil, we have several facilities in our country, but the headquarters is São José dos Campos, state of São Paulo, Brazil. We have some pictures here of the city. The city is very industrial with lots of multinational companies. And here in the bottom left, you have the main interest of our institute. So here we are in the southeast of Brazil. The mission of our institute is to develop science and technology for the outer space and the Earth system for the benefit of the Brazil and the world. We have several departments, and I just show here some of the, not the name of departments, but the areas, the fields that the departments are related to. The remote sensing, you have strong development and scientific research for Earth observation. For instance, we are responsible to provide information regarding the deforestation, the Amazon forest, also fire outbreaks in our country, emitting alerts. Space engineering, we have developed several satellites, which several are still in operation, and also have weather forecasting, climate studies, and strong also scientific and technological development. In addition, we have 7 postgraduate programs, as you can see here: astrophysics, space engineering technology, space geophysics, applied computing, meteorology, remote sensing, Earth system science, and I am related to the applied computing postgraduate program. So in this talk, we'll mention some applications of formal methods that we have worked in the past, trying to show the benefits of formal methods. So with no further delays, the first application is the mitigation problem of single event upsets in field programmable gate arrays, FPGAs. We know that space environment is a very tough environment. As you can see here in this definition of the Federal Aviation Administration, single event effects, a type of problem that can happen, occur when atmospheric radiation comprising high energy particles collide with specific locations on semiconductor device containing the aircraft systems, but also, especially in the space systems, which operate in higher altitudes. So memory device, microprocessors, FPGAs are most sensitive to single event effects. The problem is that these high energy particles can change the behavior of the device. For instance, here we have a high energy particle colliding with the substrate of a chip, electronic component. Eventually, we can change a bit that is stored as 0, can go to 1 and vice versa. And also, we can even damage it completely. We can even burn the device. You have problems when we destroy physically the device and we cannot use it anymore. So single event effects affect aerospace systems. Of course, when you talk about space applications, you usually use this kind of radiation hard components and we qualify them. But these components are extremely more expensive. And also, eventually, you want to use, for instance, embedded in a computer of a satellite to use something that is more commercial, which is eventually cheaper and even have more capabilities in terms of processing to operate embedded in the computer of a satellite. So a single event upset is a type of SEE, single event effect. An ECU, single event upset, causes a change of state in the storage cell, memory device, LED, sequential logic, is a bit flip, precisely, from 0, 1, 1 to 0. Hence, SRAM FPGAs are susceptible to SEUs. In order to deal with this approach, traditionally, it is very costly because you design and implement techniques in FPGAs and see if these techniques are suitable to mitigate the problem. So there's one interesting path is obtaining the results in the initial stage of the project using some sort of model-driven development. And by doing this, you prevent or avoid the risk to damaging the device, the FPGAs. So in the first work, the objective is to investigate the feasibility in the context of space applications of probabilistic model checking to determine what would be among a set of solutions the best technique for mitigating SEU on SRAM FPGAs. So the techniques very fast are 3 techniques. The first one is the very traditional triple modular redundancy, where you replicate your hardware design and the voltage decides if the output is okay or not. The second one is we call the scrubbing, in which you rewrite part of the memory. In this case, you correct the fault rather than masking it. In our case, you use the most basic scrubbing technique, which is called blind scrubbing. According to a time interval, we define when to copy the original data to the FPGA again. So here we can have a non-volatile memory. So from time to time, you override the data, correcting the fault. And the third one is the very famous Hamming code. It's a random correction code which detects and corrects faults. It makes use of redundant bits. We used the CTMs here, okay? Continuous time Markov chain. So it's very important to detect the event rates. In this case, the mean time between failures were the main parameter, and we use this so-called CRAM, cosmic ray effects on microelectronics. CRAM was currently supported by the Vanderbilt University School of Engineering, NASA, and the CRAM 96, a version of it, has phenomenological models to predict SEE rates. So in order to use this CRAM 96, you add information about your satellite, the type of radiation, even the type of device you are using. You add information about such kind of information, and the CRAM 96 will predict these rates. For instance, for Sirius 4A, which is a satellite that is still in operation, a very important satellite, and you have a cooperation with China, a long-standing cooperation with China to develop and launch Earth observation satellites. The mean orbital altitude is 6128.6 kilometers. The inclination is 97.8 degrees. You have the apogee, the perigee. You add all such information to the software, and it provides the rates. So here an example of heavy ions, the SEEs per bit per second. So you put this information, in this case, the FPGA, the Vortex 5, and you can see here that SEEs per bit per second is 1.28, 10 powers minus 12. So based on this, you can generate, you can create, you can deliver, can have the event rates, the fault rates of the CTMC. So we use continuous time Markov chain, very traditional model, continuous stochastic logic, which extends CTL, computation to logic, and the very famous Prism model checker. We have two case studies. The first one is a high elliptical orbit, is based on a PhD thesis of a student from Concord University in Montreal, Canada. And the second one is the Sirius 4A, our satellite that is still in operation. And in both cases, you use the FPGA Xilinx Vortex 5. So you use the CRAM 96 to determine the SEs per bit per second, and the fault event rate is precisely the lambda 1 divided by the NTBF. About the script technique was based on Hawk 16, but Hawk 16 used 2 adders and 2 multipliers in terms of hardware. In our case, we use a higher number of adders and multipliers, 10 adders and 10 multipliers. And the interval will vary from 1, 4, and 9 days. It's the time that we use to rewrite the memory. The TMR have 2 times 4-bit inputs, individual voting modules. And the Hammer code will have 4 bits of data and 3 bits of parity, encoding and decoding modules. Just very fast here, a code in Prism to the TMR. So just to mention here how we developed them, the CTMC in the language of the Prism, just to show here with no many details more. And here is an example of the cornerstone adder, which was the type of adder that we used in our evaluation in VHL, right? I believe that everyone eventually have already listened to, has already know about VHL is a programming language that you can develop hardware, different hardware projects with this programming language, and using an FPGA, you can have a very flexible way to develop hardware. You can change the hardware project of a system, just change the programming language, the language of the code of the VHL. Of course, it depends on the memory, how many gates your FPGA has. But anyway, just to an example here is the model level, higher level here, and the lower level, the code level. So the properties, we use the CSL extended with rewards. We define the 3 types of dependability attributes: availability, reliability, and safety. Roughly speaking, availability is the property of the system to be available. When you use your social network, every time you access the Instagram or something like this, it's available to you. So the system has a high availability. But it does not mean that it has high reliability. And you use here the classical definition of reliability, which is the the probability that the system is operational, for instance, 2 years from now, since it is operational now in time 0. And safety, I believe it's self-explained. So for instance, the reward property here, in the first time, which is the accumulated time in the operational mode with the interval 0t. As you can see here, we have 3 types of modes: the operational, which is the most desirable, degraded, and the most critical, is a failure of the system. Here we have the steady state probability of the failure of the system, right, which in the long run. And here we have the reliability, the probability that the system is operational or degraded in the first 3 days. And the safety, the probability the system is operational, degraded, or fail safe in the first 3 days, right? So we use here in this last 3 cases, the probability operators P and S that are defined in CSL. I will show just the results related to CBS4A. And at the end, I will present the overall conclusions about this study. Regarding availability, here we have CBS4A, and this is what we call here PUP, is indirect ionization. In this case, the ionization is induced by protons. We have a mission time of 650 days. And here we have the horizontal axis, the number of days, 650. And here we have the vertical axis, the number of days in which the system based on TMR was in one of these 3 operational modes. One of these 3 modes. Operational is the blue one, degraded is green. If failure mode, the failure is red. Blue operational, green degraded, and failure is red. So as you can see here, TMR was not good. Most of the time, the system was degraded or failure, which is not good for this technique. Regarding the Hamming code, we have the opposite behavior. As you can see here, blue one, most of the time for CBS4A in this indirect ionization, the system was operational. And for scrubbing, considering here we have the first 3, blue, red, and green, are 2 adders and 2 multipliers based on Hoek 16. And the last few ones with cyan, this magenta, and this kind of pale green, something like this, are the 10 adders and 10 multipliers, which are ours extension. For the scrubbing, with the interval of 1 day, each 1 day I rewrite the memory, we can see that the 2 adders and 2 multipliers and 10 adders and 10 multipliers were operational most of the time, which is good. The blue one here is the 2A to N, and this cyan here is 10A to N. This is good. But if we change the time interval to 9 days, 2 adders and 2 multipliers is still good. This is the blue one here. But the most complex design with 10 adders and 10 multipliers, most of the time, the system was degraded. This means that for this dependability attribute, particularly in this analysis, increasing the number of days in which you rewrite the memory is not good. But if you look at the longer run, the steady state probability, here we have the time interval in the scrubbing days, it's changed from 1 to 9. And here we have the probability of failure. You can see that for TMR, it was, again, not very good. It's a high probability of failure, 0.47. Hamming code was very good. But here, in contrast to the other case, in the long run, the 10 adders and 10 multipliers, which is the most complex design, is better as the interval increases. You can see here in the C3, the red one, as we increase in the long run, is better when we increase the scrubbing time interval. The conclusions related to availability is that Probabilistic model checking provided consistent results consider all evaluated techniques and systems. TMR, triple modular redundancy, most of the mission time in the failure mode. Hamming code has high availability, and for scrubbing, the highest time interval affecting more the smaller systems. For larger systems, it might be okay, a highest time interval. And note, you should be aware that as higher this time interval, better, because it means that I do not need to rewrite the memory more frequently. If you have a time interval that is low, is very short time interval, I should demand more time rewriting memory, doing processing that is not very important in terms of the function of the system if this time interval is lower. Regarding reliability, here we have an analysis not only with the PUP, with the indirect ionization, but also HUP, which is direct ionization. In this case, is the ionization produced by heavy ions. You have the mission time in 650 days, the same mission times, and you can see here the time, 650 days, and here's the reliability, as higher the better, for TMR and Hamming code. So you can see here the TMR, the blue one is really bad. Reliability really bad. You just with something about a few days, the reliability of the system was really bad. And the Hamming code also, here we have the HUP is direct ionization, the red one, and the cyan is the indirect ionization. But also, as the time increases, the reliability goes lower. For scrubbing, here we have another concept, what we called in this case, the cover rate. The cover rate is the probability to detect a fault since the fault exists. As higher the cover rate, it means that the system detects every fault. If you have a 100%, every fault that exists is detected by the system. So comparing here, the C1 configuration here is the two adders, two multipliers from Hawker 16, and the C2 is 10 adders, 10 multiplier hours. So you can see here, for 1 day of time interval, 100% for the C2 configuration, basically the reliability is 100, is 1, which is very good. And also for the smaller configuration, 2 adders and 2 multipliers, is also the best behavior. Even so, the reliability decreases as the time of the mission goes on. The time passes by. It also decreases, but it's the best result. But if we increase the scrubbing, here's a 1 day or 9 days, we can see that the reliability is highly affected by the time interval. We can see in the best case with the cyan here, the configuration 2, 10 adders and multipliers, the reliability is not always 1. It decreases when the time passes. But if you can see here, the configuration with the cover rate 1 for the C1, 2 adders and multiplier, the reliability drops very much when the time passes. So the overall conclusion, I will not add the conclusions here related to safety or due to the time, but the overall conclusions of this research is that using a formal methods approach to complement a traditional one can worth the value. From the 3 techniques, TMR presented the bad performance, Hamming code presented promising results. In the scrubbing, the reliability is related to the time interval, and safety is more affected by the cover rate. This was the first application that we used, in this case, probabilistic model checking. The second one is a completely different, in which we'll go towards automated unit test case generation. based on C++ source code. The second application is related to software testing, which is a activity. And the main goal of software testing is precisely to provide the means to develop a high quality software. The main intention, roughly speaking, is trying to detect the defects, the bugs of the software products. But sometimes we just have the source code with no documentation. When you talk about critical systems like satellites, like aircrafts, or some other critical system, as far as I know, at least in the aerospace community, we still use these very traditional software development methodologies like waterfall model, V model, and so on. These types of software development methodologies, they are heavily dependent on documentation. You develop lots of documentation. In some cases, in the waterfall model, you just start writing code after you have correctly defined, or at the maximum as you can, your requirements, design of the system, and so on. Just after that, you start writing the code. But of course, this very traditional methodology, they have some problems, because since every project has a schedule, of course, they have deadlines. So eventually, you lose the synchronization between the documentation and the source code. So at some point, you start writing code, because if you do not do this, you'll not meet the deadlines, and you have you lost the synchronization between what is in the documentation and in the source code. That's why in the past, people proposed these so-called agile methodologies that in general, as far as I know, they do not put much emphasis on documentation. The objective is time to market. The bottom line, one way or another, eventually you just have the source code in order to develop your tests. And we know that the unit test level is widely used in industry. We have lots of frameworks and tools available, like JUnit 5, Unit, and so on. There's also another motivation for this work. In this case here, we have this company, Tayob, that it provides some kind of, this company provides some sort of classification of use of programming language. And you can see here that the C++ programming language is the 4th place, just behind Python, C, Java, according to their report. So it's very useful still today. So the objective of the second application is to contribute to the improvement of quality of software products, creating the C++ programming language via automated test case generation and formal methods. So we developed this method, which we call Singularity, which the main goal is precisely to automate the generation for unit test case based only on the C++ source code. And what this method does is it performs successive transformation, starting from the source code. So we translate to the final state machine, after that control flow graph, and after that, the notation of the NU SMV model checker, which is a very traditional functional model checking tool. And the basic idea of this method is precisely to define trap properties to generate counter examples, because the counter examples here are the test case data, as people have been doing this in the formal methods community applying, or the software testing / formal methods community. So counter examples here are something good for us, because they are the test case data. So basically, the method have three modules called structure, generator, and constructor. The structure is, it takes a CPP code, and based on this code, it generates a finite state machine in XML notation. The generator takes this input and generate the SMV model in the notation of the NUSMV model checker, and the constructor generate the counter examples with the abstract test case data. I'll just mention here some important remarks about some of the modules. The generator module translates the generated metadata FSM into an SMV model, notation of the new SMV model checker, and the trap properties comes from the idea of a previous work that we proposed, a method called HighMost, and precisely the intention is to force the counter example generation, and they were formalized in computation tree logic CTL. The basic idea about the trap properties is the concept of the negation. The idea is that when you negate things, you generate counterexamples. So first of all, we try to use the specification patterns, and indeed, the first case here, negation of the events for all paths, always not even equal to EI. In this case, we are precisely trying to generate a counterexample saying that the last event is different from U1, so eventually you have a counterexample. If you look at here, this is precisely the, here in dry, I hope you can see it there. It's a very famous specification pattern. This is the absence pattern in global scope, AG not P, okay? This is the first one here. But the point is that we tried another patterns here, but in our case, we're not very successful in generating counterexamples using the specification patterns, with the exception of this first one here, the absence pattern and the global scope. So the basic idea is that, in this case, the second one is a negation of the Boolean transitions. In this case here, we have this alpha and beta are formulas that represent that the system is in some state. You look at the model, you see that there's a transition of alpha to beta. So in this case here is this gamma here, what's it called the Boolean transition, something like true or false. So eventually we try to force a counterexample generation when you're having the state here represented by alpha, and if gamma is true or false, we do this both case, we see that the next state is not beta. This is for all paths, always alpha and gamma implies there is some path next, not beta. In the third case, it's what we call the negation of the non-Boolean transition. The basic difference is that gamma here is not something true or false. Can assume other values. And here we split in two different situations. This case is similar to the other one here, the case 2, difference that gamma here is not Boolean. The second that we negate the transition and we keep the destination state. That's the point. These two properties here were basically obtained, these properties templates were basically obtained by experimentation based on the case studies. We developed a tool in Java and we use the anti-LR. Anti-LR is a parser generator for reading. We have several grammars developed, available, so you can use them to read the C++ source code in Java. Here is the GitHub of the tool. And we applied it to two case studies, two C++ geoinformatics applications, which are mature and, in our point of view, non-trivial applications. The first one is this called GeoDMA, which is toolbox for integrating remote sensing imaging analysis methods with data mining. We evaluated 24 classes. Each class is a unity, in our case, of GLDMA. And the second one is called the TerraLib, which is a library to construct geographical applications. This lib is very important for us. We have several applications, free open source applications related to geoinformatics systems available, developed by our institute, which use this kind of library underneath as the basis to develop these applications. It's a very non-trivial application, has more than 1 million lines of code. And we evaluated 1,063 classes of TerraLib. The results, again, we just show for the most complex case study with TerraLib. The metric is state coverage, the number of states of the model that appear in the counterexamples. Remember that the counterexamples are the test case data. In the transition coverage, number of transitions of the model that appear in the counterexamples, test case data. In the first case here, we have the state coverage here, the vertical axis, and the number of states per class, the horizontal axis. You can see here that we have classes which generate a very low number of states, but have classes that generate more than 800, more than 800 states. So if you look at this plot, you can say that up to 100 states per class, we have a good state coverage here, the top left. In some case, we have a very good state coverage if you have up to 100 states per class. Not all classes that have up to 100 will have a good state coverage. We have lots here that were not very good, but we can have up to 100 states per class. Very good state coverage in some cases. More than 100 states, the performance are not very good. And here we have the transition coverage times the number of state transitions per class. Here on the horizontal axis, we have the number of state transitions per class. Here we have the transition coverage. And again, there's some sort of magic number in our results. Up to 100 state transitions per class, we have a good transition coverage here, top left. And you can see that we can have classes that has close to 1,000 transitions per class. Higher than 100 transitions per class, the method was not very good. Here we will show a plot of the state coverage, the vertical axis, and number of generated properties per class, the horizontal axis. Because eventually, when we started to develop this work, we thought that, okay, as higher the number of properties that we generate, we believe that we will have a better performance. This was we thought at the beginning before starting this work. So we have an analysis here showing the number of generated properties per class. And again, this belief was indeed not true in our case. Again, up to 100 property per class, we have a good state coverage here. But after that, the state coverage was not very good. Same analysis relating now regarding the transition coverage here, the vertical axis in the number of generated properties per class. Again, up to 100 properties per class, good transition coverage. So generating a large number of properties does not imply a good coverage of the model of the source code. We also defined a concept which we called valid counterexample, in this case, valid test case, because as you know, these model checkers, sometimes they generate counterexamples with very few number of states. In practical terms, this means that these test cases are indeed not useful. So based on our experience, we defined that to be considered a valid counterexample, eventually something that are we really executing the future to test our software, under test our product software? The counterexample should have at least more than 2 states. Because this is based on our experience and also previous works. Less than 2 states, we considered that this counterexample test case is invalid because it is not useful in practical terms. So it should have at more than 2 states. More than 2 states to be considered a valid counterexample. So we have the total number, all counterexamples, number of all counterexamples per class here, in the horizontal axis, on the vertical axis, number of valid counterexamples. And again, up to 100 counterexamples per class, good. Higher than this, not good. On the other side, consider the invalid counterexamples, which are the counterexamples that have at the most 2 states, at maximum 2 states. At the maximum 2 states, we have the same behavior. And here we have the number of invalid counterexamples of the case-free properties. The case-free properties were by far the property that generate, the property template that generate the highest number of properties, which is this case here of the non-Boolean transitions. So case-free generate the highest number of properties compared to the 2 previous ones. So if you can see here, these are the number of properties of the case-free per class, number of valid counterexamples. So basically, we have lots of invalid counterexamples in this case. What are the overall conclusions regarding this second application? This singularity method was effective. I mean, we can consider that it generated effective counterexamples, generated effective counterexamples, test case data up to 100 states per class, and 100 transitions per class. Generating a large number of properties does not imply a good coverage of the model source code. We have lots of invalid counterexamples, particularly due to case-free. So it's very important to carefully choose the properties templates in order to derive more meaningful counterexamples. I mean, more meaningful, more feasible, more valid test case. As I have just mentioned, we tried some properties templates based on the specification patterns, as I showed you in the website. But in general, no good results considering our case studies. Finally, the third application is again completely different of the two previous ones, which is the assessment of the safety of navigation systems for aircrafts. This work was developed by a very experienced engineer of a very famous Brazilian company, the Embraer, that is, the headquarters is here in São José dos Campos, close to our institute in the same avenue. In fact, you can reach both institutions, INPE and Embraer. And I believe that the main interesting point about this third case study is the level of detail of the models in order to assess the safety of navigation system for aircrafts. So safety assessment, system safety assessment. Safety assessment is mandatory for certification of aircraft complying with Part 25 airworthiness standards. Airworthiness is a measure of an aircraft's suitability for safe flight. Here's just an example of one jet produced by Embraer. We have lots of guidelines, documentations related to system safety assessment. Includes the Federal Aviation Administration AC 25 14091A1B and SCI ARP 4761. So these guidelines predict several methods for compliance demonstration, such as failure mode and effect analysis, failure hazard analysis, fault tree analysis, which is still one of the most popular, eventually the most popular, at least talking to this engineer, one method that they use a lot at Embraer. So we have FMEA, FHA, FTA. But predicted in the SCI ARP 4761 guideline, it predicts the use of probabilistic models as an alternative to the traditional fault tree analysis. What are the advantages of probabilistic model checking that we used again over FTA? You can express a temporal sequence of events or state-dependent behavior of systems by using probabilistic model checking. And also, we have possible automation on certain parts of the safety assessment activity. So the objective of the third study is to investigate the contribution of formal methods, particularly probabilistic model checking, to the activity of assessing the safety of aircraft navigation systems, providing an alternative to complement, this word is very important, the study carried out by using classical but non-formal methods. So this is a lot, of course, lots of all this such information is in the paper. Here we present the relationship between the probability and severity of failure condition as per this guideline here, AC 25-13091B. So we can see here that we have the failure condition, no safety factors. So this is something that the passages just provide some inconvenience. We have minor physical discomfort, major physical distress, possible including injuries, hazardous, serious or fatal injury to a small number of passengers or cabin crew, and catastrophic where you have multiple fatalities. And here we have the allowable qualitative probability, no probability requirement, up to extremely improbable, and the allowable quantitative probability as we expect if you design an aircraft, a system. Of course, we do not want that a catastrophic failure happened. So eventually, of course, this probability for catastrophic failure happens should be very lower, because with this, you guarantee that the system is more safer. As you increase the failure condition level in terms of severity, you decrease the allowable probability. So here the hazard classification for the subset of aircraft position navigation, because in our case, the goal is that the case study, our safety system assessment was for navigation systems of a generic commercial transport category aircraft. Okay, so what we, this AC 21380, what you can see here are the failure conditions, loss of navigation and misleading information. And here we have what we call the operations. Each failure condition, loss of navigation, misleading information, is applicable to a certain type of operation, mostly related to approach procedures, navigation related to landing. So these operations are mostly related to approach procedures. As you can see in the next slides, in a typical flight, the most critical phase are during the landing of the aircraft. You can see here. You can see this in the next slides. So here we have the operations, unhooked terminal area, non-precision approach, LNAV, or RNP 0.3, The loss of navigation is no effect, measure, this is impact that you have, right? Measure, 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 and the misleading information, you have minor, major, major hazard. So we have an on-road terminal error, non-precision approach, LNAV or NNP 0.3, non-precision approach with vertical guidance, LNAV, VNAV, LP, LPV approach, GLS approach. If you look at the paper, you see a brief definition of all such operations. I would just mention here the first one, the on-road terminal error non-precision approach is essentially the capacity of the aircraft to determine its lateral position, latitude and longitude with the appropriate level of position certainty. LNAV is a mode of operation where the aircraft relates to trajectory is typically controlled by the flight management system, which is one of the subsystems of the avionics electronics. And required navigation performance RNP 0.3 is a similar mode, but it has a stricter position certainty limit of 0.3 nautical miles. So this is the high level system architecture, which is not it's a simplified, but in my point of view, is not as simplified. Here we have subsystems. For this, in the flight management system, we see that we have two flight management systems here. We have display units, very important to provide the quality information to the pilots. We have air data system. We have the inertial reference system, IRS here, 1, 2, 3, right? And GNS launch system, GLS here, GNS, and so on. So we have several subsystems in the high level system architecture. Here we have the avionics bus. This is a report that shows the flight phase exposure times. It's precisely what I have just mentioned regarding the phase, the critical phase, when you talk about fatal accidents and onboard fatalities. If you can see here, it is a 1.5-hour flight, and the critical phase, which accounts for almost 50% of the fatal accidents and onboard fatalities, are due these two phases, the final approach and landing. And look here that these two phases only accounts for 4% of the 1.5-hour flight. That's a very critical phase in which the accidents can happen. So the CTMC models, again, we use continuous time Markov chain. We use the CSL again, in this case. In this case, the CTMC model have this phase, right? We have the takeoff, we have the climb, we have the cruise, we have descent of the aircraft, which in this case can be capable or not capable. If it's capable, you select an approach. If it's capable, the aircraft successfully land, and you have the pre-flight, and the aircraft can go to another flight. But if it's not capable here, for instance, you can select an alternate approach, one of these 4 approaches, for instance, that I mentioned, and can try with this alternate approach. And again, if you miss this approach here, not capable here, so you can select another alternate approach and trying to successfully land the airplane, the aircraft. Just to show a piece of the PRISM model, which shows the flight phase state transitions in PRISM. You can see here the flight duration is 1.5 hours, and the mean time spent with flight phase, they come precisely off this plot here. For instance, 1% is takeoff, 0.01. 15% is time in climb, because we join here initial climb with climb 1 plus 14 to 15. 57% the cruise, and so on. Okay, and the phase we indicate is 0 pre-flight, 1 takeoff, 2 climb, and so on. And you have the code in PRISM, that represents the phase, the transitions, right? 1 divided by the time is the failure, the event rate, So based on documentation of the equipment, we have, and also in the experience of the engineer, we have the equipment failure mode rates. We model these 6 subsystems: FMS, GNSS, IRS, DME, ADS, GLS. I showed the high level system architecture. The failure rate per hour, 10 powers minus 6 here for FMS, and the erroneous rates per hour, 10 powers minus 7. All systems subsystems start as healthy in this state and may present one of 2 possible failure modes. They may become failed, which we call as annunciated fault, or may present erroneous information, which is a non-annunciated fault. It starts healthy, but they can change to this kind of state transitions, to these two types of failure modes. Very briefly, just to mention here some of the code of the IRS, the others are similar. Okay, you show here the failure rate, erroneous rate, and so on. And here we have the module, okay, in Prism, just to show piece of the code in Prism. Regarding the characteristics of the CTMC models, we developed a model for each one of operation. For each one of operation, develop a model and the properties, of course, in CSL. So the smallest model is related to LPV, which has something about 16.7 thousand of reachable states and something about 146,000 of transitions. And the largest model is for VNAV, which has something about 4.3 million of reachable states and around 60 million of transitions. These are characteristics of the CTMC models, and we developed one for each type of operation. The safety properties were defined in CSL, and we have 2 types of failure conditions, as I have already mentioned: loss of navigation, but the most critical here is what we call the misleading information, where the system indications are erroneous to a point where the pilots could be misled, which may be a more severe failure condition, because, for instance, if the pilot has a wrong indication of altitude, eventually when it the aircraft can be very close to the Earth, and the pilot is thinking that it is operating in higher altitude. This can be very complicated for the safety of the aircraft. Just to mention the safety properties for this, for loss of navigation, the loss of navigation safety property for the LNAV RNP 0.3 approach, we have the probability should be lower than 10 powers minus 5 times t, eventually en route terminal in loss of navigation. And a similar for the misleading information safety property, this probability should be lower 10 powers minus 5 times t, eventually en route terminal approach and misleading information. I would like just to mention here that the bounds of the probabilities depend on flight time, duration time. If we increase or decrease the duration time, of course, the bound changes. And just to mention here, similar for loss of navigation safety properties, for the GLS approach, is something similar. Probability should be less than 10 powers minus 5 times t, eventually phase H. This phase were defined here. Okay, missed the approach. And in the other case, the misleading information for the GLS approach, probability should be less than 10 powers minus 7 times the time. Eventually, phase 5 is misleading information. Phase 5 here is the approach. So the results were very good. You can see here for the operation, the 4 operations that we modeled in the failure mode, failure conditions, the classification just repeating. The objective means the maximum acceptable probability that the system should present. So of course, to be compliant, the probability should be lower than this number here. So you can see that the probability that we got from by using Prism and all these models and CSL properties, which lower than the maximum acceptable probability, which means that the design of this aircraft, based on these rates, based on the transitions, based on the rates of the equipments, okay, were okay. So eventually, if this is done in the beginning of the development of the system, eventually in the close to this, basically the system engineering or something like this, the initial development of the subsystems of the aircraft. So the design is okay. And we extend the flight duration from 1.5 hours to 18 hours. At that time, this was the longest flight that we were aware that exists. Is a one non-stop 18 hours, and it's still okay. Just here, but for the other modes, the results were similar. The LNAV RNP 0.3 loss of navigation was T equal to 18 hours. The probability is still lower than the maximum acceptable probability. Remember, in this case, we changed the bounds of based on the flight duration. The overall conclusion regarding this third application is that probabilistic model checking is feasible for the activity of assessing the safety of aircraft navigation systems, but of course, we must not neglect the classical methods like FTA and so on. To conclude this talk, my final remarks and some observations based on our experience is that formal methods, in that case, probabilistic functional model checking, I believe that they were used with lots of success, considering non-trivial applications, 3 different applications. This is good, in my point of view. But in my point of view, eventually someone in the audience may contradict or may not agree with me. In the current stage, formal methods should be used as a complementary approach, adding non-formal classical solutions. I still believe that it's very hard to use formal methods, consider this a very complex system, consider the entire very complex system, which is related to my third remark. It seems that to me, scalability and lack of transparency still seem to be big issues in the practical settings related to formal method. At least in our experience in talking to some guys in the industry, it seems that there is still a problem. And a last remark is that in practical terms, be formal, but not so formal. What I want to say about this is that we have very good results in my point of view, but sometimes we need to relax a little. If you want to be very formal with, for instance, all the transformations that we do during the process, eventually we will not achieve your deadline. Of course, I'm not saying that all the analysis, of course, they are very important, but eventually we need to be cool, relax a little in order to get the results. The reference here, this is the first one, is the Federal Aviation Administration about definition. This is the work, the second one, the Hook, is the PhD thesis from the Hook, Concordia University, Montreal, Canada. This is, the third one here is related to the first application, SUs in FPGAs in the paper, is the master dissertation from my student. first application, SAU's FPGA. These are the paper and the master dissertation related to the second application, automated unit test case generation for C++ applications using model checking, paper and master dissertation. And this is the highmost which we use it to generate the ideas, to generate the trap properties for the second application. And this is the third application paper, the guy from Embraer. Just a remark, this paper here, the aircraft navigation system was awarded in this conference, which is a very traditional conference, not a formal methods conference, a conference, computational science and applications in 2021. I would like to thank you very much for this opportunity. It was a great pleasure to talk here. You can see here my email, my personal webpage, where you can see my current research fields. I'm most interested today in machine deep learning, artificial intelligence, optimization, software testing, but of course, still relying on formal methods to help software testing. And I also have here my GitHub page where we put some code that I am working, I have been working recently. Thank you very much for the opportunity. And if there is some questions, I am available. Thank you.
Thank you so much, Valdivino. It was a very interesting talk. I think we start very good with your talk. You've shown several applications by you using formal methods in industry and actually with practical things in software testing, aircraft and satellites. So it was really interesting to see all these usages of what we'll be discussing. So sometimes we really focused on doing the theoretical part or the formal and don't see an avenue where it could be used. And here in your talk you have shown several applications, and I think it was very interesting. We had some questions in the chat. I'm going to start with the chat questions, but also after I do this, please feel free if you have some questions to Valdivino as well. We have about 20 minutes for questions, so it's quite a reasonable time. So the first, I think Juliana did some questions regarding the first application and the third one. So regarding the first application, she asks, how is the model how is the model in Prism? Do you translate VHDL to Prism language? This is the first. And the second question is, how do you represent the techniques, for instance, scrubbing? Do you need only probabilities or some behavior of the technique as well?
Regarding the first question, no. We looked at the principles of the techniques and we implemented them in the Prism. Okay, the first point. But I must mention that because of the time, I will just put here the dissertation of my student. And can you see here my no?
Yes, we can.
You see? Yeah. It is in Portuguese.
Oh,
okay?
Yeah, indeed.
Okay, but we compared the model checking approach with the model sim, the symbol of functional simulation. This is what people use traditionally that you can use them. So we compared this also with the functional simulation, and again, our approach got very, very interesting results. The point is that we looked at the behavior of the techniques implemented in Prism. Okay, but after that, in a true project, based on the modern prism, you can go and translate to VLTL and use the true FPGA. Interesting point is that you can translate this automatically, right? From Prism to VLTL. Eventually, I don't know if there is some tool or some approach that can do it. The second question is about
how do you represent the techniques, for instance,
okay,
in scrubbing? Do you need only probabilities or the behaviors as well?
the best thing to do is to show the code. Let me see, please. I'll try to show here. Okay, we're talking about scrubbing. Scrubbing not here. Yeah. Hemming. Oh, yeah, not put here. Just to the prism here. Here's the code for TMR, for instance, but what is the properties? Can you see here? It's having a slow, but can you see here the screen?
Yeah, no? It's a little bit small, but yeah, I think we can.
But the point is that it's precisely I believe it's better to show the here. The point is that if you can see here, in our case, we asked Prism to get the value of the probability. Okay, when you put the question mark here, it's different from the third case. The third case we define precisely. Look, the probability should be lower than 10 times. Should be lower 10 powers minus 5 times t, with t as duration of flight. In our case here, we got the values of, we asked Prism because this is something that is not in CSL, okay? You know that this is the question marks when you, it's something related to Prism. So in this case, we asked the model checker to say, look, what is the probability if this always 0t operation order grade? So it got the probability, okay? Also in the long run, and here the reward you get a number. That's the point in this case. But as in the code here is small, but during the code, we just do the logic representing the number of adders and multipliers that we have. We have some formulas and the modules and also rewards here to get the numbers when they pass the time failure state. That's the point. Just the basic difference from the first, the way to, I mean, to get the properties, the probabilities in the first and third case study. In the first case study, we asked Prism to get the value of the probability in order to generate the plots. In the second case study, no, we know precisely what should be the probabilities based on the equipment rate. So we can define, look, the probability should be lower than the bound. Okay.
Okay. So yeah, indeed you have some model, some behavior there as well. And she also asked some questions about the last work. So how the architecture, for instance, subsystems and buses was considered in Prism when you model the aircraft behavior. And the second is, did you explore the influence of system redundancy to achieve the desired probability?
Okay, let me see. I believe that here is better to, the eventually this is better here. Let me show the code, which is better. It is better to show the code. Let's just see. For instance, let me show the LNAV VNAV here. Not model. Not eventually, if I want to put here, eventually you can have a. It's better to see now.
Yes, it's better now.
So this is for this the model for LNAV VNAV. So here we have the flight duration phase. Okay, as I showed you, right? The phase transition, and here we have the formulas for the laws of navigation, and the misleading information, right? And so we have there, for instance, here we have three IRS, Industrial Reference Systems, just changing, doing this imprisonment, right? Failure 1 and failure 2 or something like this. So we have redundancy in this way. Three IRS, we have 2 GNSS, and we have 2 flight management systems here, you see? And so on. So that's why how you add the redundancy, trying to be as much as possible with this architecture defined here.
Okay.
And what are the other questions?
The second one is about the redundancy, and the first one is how the architecture of the subsystems and buses was considered. But I think you just showed that.
Yeah, I just showed it here. Okay, so here you can see just about transitions regarding the failure rate, edge failure rate, and see the transitions, right?
Yeah, indeed. Okay. We have Sofiane, you can please unmute yourself and please ask your question.
Can you hear me?
Oh, your microphone is quite not good. Yeah, there is some problem with your microphone. Yeah. Can you try doing? No, we can't. We can hear your voice, but it's quite robotic. Yeah. There's something wrong probably with your microphone. Yeah.
You
can open now we can. Yeah.
Okay. All right. So congratulations, Valdivino, for your best paper award. Nice to hear that. I have actually a couple of questions, quick questions. The first one is, you have chosen to model the failures using CTMCs. However, have you considered using like fault trees or reliability block diagrams as a model for failures?
No, we did not. We did not. I know that there are some works people have been using for fault tree, something like this, but we tried to go right to the Prism, basically, in my point of view, because Prism is very easy to use. So I believe that the guy worked very, very much with fault tree analysis, and eventually you can try to do this, but he thought that it was more direct to try to explore directly in Prism and CTMC, and rather than trying to do this. We do not.
Yeah, there exists some model checkers, for example, supporting fault trees.
Yeah,
but that would be an avenue to explore. My other question is about state space explosion. I mean, you used Prism also in the other application you used, like, in USMV. I mean, have you experienced situations where you were running out of memory because of the state space explosion?
No, in this case, no. Up to this number of states, not only in USMV, but also here, we did not expect. When I was visiting you in Montreal, I got even something about in Prism with a traditional laptop with something about, as far as I remember, something about 30 million reachable states, and something about, I don't remember quite, 100 or 100 million transition. That's okay. we did not expect this problem. And but of course, one thing that the guy, as I expected this, the guy told us, look, I can't use this for the entire aircraft. I have to simplify a lot in order to get the result. This is the problem of scalability that we still have, in my point of view. But eventually, there is some kind of tools that can do work properly. But in our case, we did not get doing this kind of something like divide and conquer, right? Do it by models, by each operation. So you were successful to get results in good, in reasonable time for our case. That's the point.
So you're not considering using like theorem proving, like our colleagues at NASA?
To the field improvement, the point of field improvement, when I was listening to you, I think you still have a very good group, right? In field improvement, all guys were working with Isabel Hall and something like this. The problem, Sofiane, is precisely trying to get people to work with this.
Yes.
Today, even model checking, if I think that is something easier, it's very easy to use Prism. I don't know in Canada, but at least here, even that we work with critical applications, some today is very hard to find people. So the point of field improvement is very nice, but it's very hard, at least here in our institute, even knowing that this is very important to get people. So the point is that, yes, of course, especially when I returned from the visit in Concordia University, but it's really hard to find people. It's not about the technique. It's about to get qualified people that have background and have interested in using. That's the point.
Yeah, the same here. I mean, you can be trusted.
Yeah.
Okay, thank you, Valdivino. Thank you.
Very nice to hear from you.
Yes, thank you.
Yeah.
Yeah, thank you, Sofiane. And I had some questions, but now that you mentioned that for you it's easier to work with model checking, I was wondering how was the acceptance of the people from Embraer or from INPE to work. Could you comment a little bit if the willingness to code something in Prism, and how easy they think it was, and or how difficult actually, because we have this issue with formal methods as well, because people from engineering, from system engineering, for instance, they more use it to work with diagrammatic languages. So when we go to a more formal notation, we have some resistance. So could you talk a little bit about your experience in this regard?
Yes, the point is that at least with this guy, he was in a course which I used to give here, precisely about probabilistic model checking. So for this guy he told me it's very easy to use Prism, okay? And I think that my belief is that, of course, that companies like Embraer, they know the importance of formal methods they want to use. But again, I believe that even if something like Prism is very easy to use, okay, we still need, in my point of view, to go to this point here, the lack of transparency. If you do something still, and I know that there are lots of work here, for instance, in Brazil, that try to do this. If you allow some kind of even easier notation, graphical notation, or even some supported by natural language, and to translate that to Prism and automatically generate the properties, and automatically give the result, This is something that is more attractive to the guy. I have an example here that we tried in the past using for people using state charts, which is someone did not consider, but I consider a formal notation, which is as easy as Prism to use. But you know, it's something like 15 years ago, and the guy will not call me to use state charts because they do not have time to learn a new notation. For easier it is this notation, right? I believe that the transparency scalability transparency is something that, in my point of view, the community should go towards. Also, regarding scalability, I don't know if the community, probably someone is doing this, because one of the main interests, my main interest today is deep learning, artificial intelligence, and you know, these people have these frameworks like PyTorch and TensorFlow. They use the GPUs, the graphical processing units, and this is boosting a lot. This is precisely how the field today is very hot, because you can scale the training of the networks by using the graphical processing units. Eventually, I don't know if probably there is some tools, but eventually, if you want to address the scalability issue, eventually you can try to produce frameworks that can use the GPUs of the graphical processing units of your notebook, and you can scale your formal methods application. This is something that I think that should be nice to explore in the future, but eventually someone has already been doing this. Well, the point is that scalability, lack of transparency, in my point of view, should be addressed more and more. And if you can do it, just providing what we call a coffee machine approach. You put here some very easy non-formal notation and provide the results to the engineer and the system engineering phase. This is something that can boost the formal methods field for a wider application in the industry. That's my point of view.
Great to hear that from you. Yeah, thanks. And I think we have time for one more question. Anyone? Let me check the Discord. Yeah, actually, I think we're reaching the limit. Yeah. So again, and Valdivino, would you mind sharing your slides with us?
Of course.
Thanks. I'll send you an email. Then we can later put the slides on the conference page. Okay.
Okay.
And it was also very good to know that the Embraer aircrafts, they are safe enough, right? They respect those properties. Yeah. And yeah, especially here in Europe, there are lots of Embraer aircraft here. Yeah. So it was very nice as well to see that in the end. But again, I would like to thank you, Valdivino, for his availability and for his talk. Was very interesting. And we just to remind you all that we have a break now, right? Or let me just check the program. We have half an hour break, and then we go into another room. So those who received the email from the organization, the technical session will be in a different Zoom room. So be aware of that, okay? And we see each other. I hope to see you all in half an hour. Thanks again, Valdivino. A virtual applause to you and to your talk. It's really a pleasure to.
Thank you very much. Thank you very much.
Thank you, Valdivino.
Thank you.
Bye-bye.
Bye-bye.